In previous video, it has been shown that the shapes of y function and s function don't change significantly when imaginary part of their input is higher than a threshold. Now we will explore the implications from anomalous zeros of zeta function to the shape of y and s functions, if they exist. The plots below shows the symmetrical version of those functions. In these plots, d is the variable being plotted on horizontal axis. It represents real difference between the input of zeta function and the critical line. C is a constant value for the plots. It represents imaginary difference between the input of zeta function and the real line. In these plots, C equals 1 million. Both C and D are real numbers. For any point on the critical line, D equals 0. Y function produces negative infinity, because S equals 1 minus S conjugate. Any non-trivial zero also produces negative infinity of y function. Any non-trivial zero outside of the critical line, if they exist, would also produce negative infinity of y function, which would add extra legs on the curve of real part of y function. Those legs would be symmetrical about the critical line, due to functional equation of zeta function. The imaginary part of y function would switch by pi at each of those zeros. It shows that the zeta of s is located at the opposite direction of zeta of 1 minus s conjugate when s is very close but not exactly on the critical line. Anomalous zero of zeta function, if they exist, would add extra legs on the curve of real part of y function. Those legs would be symmetrical about the critical line. The imaginary part of y function would also switch by pi at each of those zeros. In this plot, the extra legs are produced by the additional term highlighted in the equation. The true anomalous zeros of zeta function must cause these extra legs appear naturally in y function without this additional term. They must be strictly generated by merely changing the value of c. For any point on the critical line, d equals 0. S function produces 0, because S equals 1 minus S conjugate. Every non-trivial zero on the critical line also produces 0 of S function, even when zeta of S equals 0. You may have heard that 0 divided by 0 is undefined. But it doesn't apply when the numerator and denominator are related to each other. At this point you must be familiar with how gamma function and the functional equation of zeta function can cancel out zeros produced by sine function for positive even integers. These are examples where 0 divided by 0 is defined. On the left plot, x squared divided by x equals 0 when x equals 0. On the right plot, 3 times x divided by x equals 3 when x equals 0. On the left plot, 3x to the 4th divided by 2x to the 4th equals 1.5 when x equals 0. On the right plot, 3x to the 4th divided by 2x to the 5th equals complex infinity when x equals 0. On the left plot, sine of x divided by x equals 1 when x equals 0. On the right plot, 1 minus cosine of x divided by sine of x equals 0 when x equals 0. A pattern shows up from these examples. When a function of a variable is divided by another function of the same variable, while both the numerator and denominator are equal to 0. The result is equal to the derivative of the numerator divided by the derivative of the denominator. Let f of x equals a of x divided by b of x. If a of x doesn't equal 0, or b of x doesn't equal 0, use the numeric value of the function. If both a of x and b of x equal 0, check their first derivatives. If both a prime of x and b prime of x also equal 0, check their second derivatives. If both a double prime of x and b double prime of x also equal 0, check their third derivatives. And so forth until at least one of them don't equal 0. Then use the numeric result. Let's get back to the last examples. On the left side, the first derivative of sine of x is cosine of x, while the first derivative of x is 1. Thus f of 0 equals cosine of 0 divided by 1, which equals 1. On the right side, the first derivative of 1 minus cosine of x is sine of x. The first derivative of sine of x is cosine of x. Thus f of 0 equals sine of 0 divided by cosine of 0, which equals 0. This is an example where the first derivative of numerator and denominator are both equal to 0. It's the same function like the last example, but the denominator is modified to the second power of the sine of x. The end result is determined by the ratio of their second derivatives. In this case, it's a half. This is an example where the first derivative of numerator and denominator are both equal to 0. The end result is determined by the ratio of their second derivatives. In this case, it's complex infinity. Now on the left side, the numerator is squared while the denominator is cubed. The result is 0. On the right side, the numerator is squared while the denominator is raised to the fourth power. The result is a quarter. You can check the results using the rules described previously. With the problem of 0 divided by 0 is out of the way, let's analyze how the behavior of S function can be used to solve Riemann's hypothesis. For the sake of the argument, let's assume that there exist anomalous zeros of zeta function, i.e. non-trivial zeros outside of the critical line. How would this affect the shape of S function? For simplicity, let's use symmetrical version of S function. Anomalous zeros imply that zeta of S equals 0 while d doesn't equal 0. The consistency and the regularity of the shape of S function for high imaginary values suggests that even when anomalous zeros are involved, the shape of S function doesn't change. It would maintain the nearly straight line with negative slope. The real part of S function consistently produces 0 when d equals 0, regardless the value of c. It still produces 0 even when zeta of S equals 0. But in this case, the imaginary part switches between negative pi and pi. It implies first derivative of zeta of S divided by first derivative of zeta of 1 minus S conjugate equals negative 1. Anomalous zero of zeta function, if they exist, would be symmetrical about the critical line. Those additional zeros will show up on both the numerator as well as the denominator of S function. In this plot, these anomalous zeros don't change the shape of the plot. The true anomalous zeros of zeta function must appear naturally without this additional terms. They must be strictly generated by merely changing the value of c. Yet, they are not expected to change the shape of S function. It was shown in previous video, that the ratio of zeta function of a complex point and its reflection about the critical line follows a smooth curve. In this case, d equals 0.1. There is no obvious reason to suggest that it will deviate from the trend at any finite point. Note that these curves are plotted along the imaginary axis. Curiosity aside, you may wonder why we take the more complex route to convince the non-existence of anomalous zero of zeta function using its ratio instead of its difference. Y function can reliably detect anomalous zero by getting additional legs of negative infinity. It's certainly an anomalous curve of Y function, but we can't say that it's impossible only from this observation. S function reliably gets closer to a straight line with negative slope as the imaginary part of the input is increased. We should be able to prove this fact by processing the nested infinite sums as the definition of S function. But it's not sensitive to zeros of zeta function, including the ordinary non-trivial zeros lying on the critical line. In the next video we will introduce a new function combining y and s functions to get the advantages from both. From the shape of the curve, it will be conveniently called v function. These functions can be used to build an overwhelmingly strong argumentation against the existence of anomalous zero of zeta function, and ultimately prove Riemann's hypothesis. Don't forget to push the like button and subscribe to this channel so you don't miss the next videos. Thanks for watching.